When last we met, we were looking at the Follow the Knob program, and let's see here. Yeah. All right. Actually, let me. I mentioned the two ways of doing the program. I am going to go over the second way to do it. The second way is to, in the start routine, that's messed up. In start, define and populate an array. In RAM. Now, when we went over arrays in the data structure section of the course, an array is a one-dimensional structure where all the elements have the same size, and you calculate the position based on the index and the size of the elements. So, in this instance, you're going to do a 2-byte elements, and they're going to have the values 1, 2, 4, 8, 16, etc. to 128. How you do that is with a for loop type of structure. You loop and you start with the value of 1. Loop, and then each iteration loop 16 times, or 15, 16 times. There's a 15 times. Come on. 15 times, and multiply your value by 2 each time. Now you can multiply by 2 by doing a logic shift left and a rotate left into the high byte with each. Start with 1 in the value of the array, because the array, the 2-byte elements represent the values on ports A and C for the output. so one light has to be on each for each value. So that would correspond to the binary of values of 1, 2, 4, 8, 16, etc., 32. Oh, I'm sorry, it's not to 128, it's to 32K. Loop 15 times, multiply by a value of 2, and then store that value in the array. And end loop. So you're going to want to use pointers for this. Arrays you need to have the pointers. So for LDI R26, you're going to have 0x00, and LDI R27 0x40, which would give you an address of 4000. That is the starting address for the RAM for this chip. It's loaded and stored just like the peripheral registers. It's just RAM instead of configuring a peripheral. The addressing is done the same way. The loading and storing are done the same way. So when you have the pointer to store from the pointer, or to the from the pointer to the data space, you just do ST. And then X is the destination. The X, this is the X pointer. And then say R16 for the low byte. And then you put a plus after it, after the X, to make it auto increment after you store that. And then you do another store, X plus R17 for the high byte. And then that will put the pointer at the next element of the, so that would store R16 at 4000, store 17 at 4001, and then the pointer would be at 4002 for the next element to be stored. So that's how you use the pointers in assembly. You load the address that you're going to start dealing with, and then store them in order. And then accessing them later, you would load the base address, and then LD, let's say R16 destination, X plus, and then LD R17 X. Oops. Because you'd only be getting one element, which is 2 bytes. So one byte into the low byte into R16, the high byte into R17. So let me put this in more solid, concrete structure here. In the start, oops. You would have, let's see here, LDI R16 0x00, because this is going to be your counter variable for the for loop, your counter register. LDI R17 0x0f. The limit of the loop then let's say LDI R18 0x01. The low byte of element LDI R8 or 19 0x00. The high byte high byte of element LDI R26 0x00 and LDI R27 0x40. X pointer base address. Base address of array. So, loading a lot of constants into registers, getting set up for the for loop. And then, about caught up? Yeah. Then you start your loop. Loop. You would compare R16 and R17. BREQ. If they're equal, end loop. Logic shift left R18, ROL R19. You got from the We covered those from the last class session. And then store x plus R18, store x plus R19. Increment your counter register, which is 16, and then our jump loop. And then you would have loop end loop, the end loop label here. So this constitutes your for loop. These two generate the data. And these two store the data. In RAM. Inc is increment. And yeah, so that's your for loop to define the array. You might want to have this begin loop, because loop is also used in the main loop is typically called loop. So I'll call this begin loop and our jump to that. So when 16 is equal to 0, it'll go through and that's not right. It wouldn't store the first one. The first. It wouldn't store the first LED being on, because it would logic shift so if you take these and move it here, then you could, the final store of them, when it's equal to 15, oh no, make it make it 16. Let's see here. Come on. Make it, make this 16. And then do the store before the logic shift and rotate left. And the counter would count up one extra. Does that make sense? Yeah. When it reaches 15, it'll go through the loop. And then on the 16th, it'll break out of the loop. When it's reached a 16, it'll break out of the loop. So, yeah, put the store before the logic shift and rotate left of R18 and R19. And that should populate your array. Now, when you get the data from the ADC to indicate where to turn on the light, say your ADC ready routine, you'd read LDS, let's see here, it's a R20, 0x0610, if I'm recalling correctly, the address for the ADC result ready. And then LDS R21 0x0611 to get the high byte. So get ADC result. And then, like you did on the variable blink program, check if equal to previous value. And when you update, you would LDI R27 0x40, the high byte of the address for the pointer, the X pointer, the high byte. Now the low byte you have to calculate from the high byte of the ADC result. You have 16 values in the high byte, 0 to 15, right? We went over that a couple of class sessions ago. And you multiply that by 2 to get the index location, the address location of the array element that you want, because you multiply it by the size of the elements of the array, which is 2 bytes. So you LSL R21 to multiply by 2. By 2. And then move from to R26 from R21. And this sets high byte of X pointer. And this sets low byte of X pointer. So if the high byte of the ADC is a 0, multiplying by 2 won't do anything. It'll still be 0. So the low byte would be 400. The address would be 4000. The pointer to the base address of the array. And then you would LDR, let's say 22, X plus LDR23, X, and that will load the element into the registers. All right. And then once you load them into the registers, just store these two values out to ports A and C out registers. The out register of ports A and C. Yeah, we're doing on time. Okay, we got time. One slide? Yeah. Mm-hmm. I'm sorry, what? Oh, okay. So once you've loaded it into R26, 22 and 23, you would STS 0x0404, I believe is the address of our, and then is it 22 and 23? Okay. 22 and 0x0444 R23. Sends the array element to ports A and C. Did I say it was at 120 points if you do it this way instead of?
Yeah, you said
120? Okay, I thought it was 120. Yeah, if you do it this way and get it to work right. Yeah, and we got about a week and a half to get it programmed in right. I have yet to see somebody attempt this and get it working right in the few times that I've taught this class before. So looking for a first. But anyway, that's the gist of it. You load all the possible combinations of lights into an array, 2 bytes per element. Then access that array based on the value from the ADC, load the value from the array, and send it out to the ports. So the setup time is a little bit longer. That's where the for loop is. But the accessing putting the right outputs out should be faster. It should be slightly more snappy. But not that we would be able to notice it. It would probably be maybe a couple hundred nanoseconds difference in the response time. But yeah, that's the gist of the alternate way of doing things. Any questions about it, or anybody thinking about trying it? Maybe, maybe not. All right. Of course, you could always do the first one, and if you have time, if you get that working and you have time, you can do the second one. So I'll allow that. You know, if you turn in the first one and then make the second one by the deadline, which is the 22nd, then I will bump up the grade. But yeah. Any questions about this or the other way to do the programming project?
You've done it like that in a Word?
I'm sorry?
You've done it like that before in a Word?
Yeah. It's a little bit more complicated. That's why I'm giving extra points for it. But you know, it's getting you how to really handle the nuts and bolts of an array, as well as getting familiar with how to implement a for loop in assembly. So it's a good learning exercise. Yeah, but yeah, that's the whole point of these classes, is to learn stuff and learn how things work on the inside. So you know, if you ever need to, and you know, as you're programming at a higher level, you know what's going on underneath the hood. It's helpful. You can program more efficiently, that sort of thing.
Have you tried doing the array method?
Yeah.
How long take it?
I don't know. I don't remember. It's been a couple of years since I did it. Yeah, I should find the program and see if I could find the program in some of my old files, maybe on an external hard drive somewhere, or something like that. Or I could just redo it and implement it again. But yeah. All right. Well, I guess that'll be it for the day. Sorry about Wednesday's. Do you have a question? First slide, sure. There you go. I'd like to apologize for the video from Wednesday. The audio cut out on it for some reason. There was audio at the point where I was doing roll and all that sort of stuff, and then when I was starting on the lecture, the audio cut out, and So, but it has been requested that I put it up anyway. So I will edit it and upload it to YouTube probably this afternoon. So anyway, all right, have a good day. Have a good weekend. See you on Monday.